The idea of a space elevator is simple. It's beautiful, even. You build a tower, or more accurately, a cable that goes straight up. It goes from the ground all the way into space. Then you just climb it. No rockets, no explosions, no throwing away massive expensive engines. You just get in an elevator car, press the up button, and ride to orbit. It sounds like science fiction. And for now, it is. But the question is, could it ever be real? Is it a feasible idea or just a dream? The answer is complicated. The physics behind it are sound, but the engineering is a nightmare. And the human element, the politics and the money, might be the hardest part of all. To understand if we could ever build one, we have to look at how it would work, what it would be made of, and all the ways it could go terribly, catastrophically wrong. Let's start with the basic design. You can't just build a tower 100,000 kilometers high. It would collapse under its own weight before you even got close. The space elevator isn't a structure that stands up, it's a structure that hangs down. The concept relies on a delicate balance of forces. First, you need an anchor. This would be a massive station on the ground, located on the equator. It has to be on the equator because that's where the Earth spins fastest. This spin is crucial. From the anchor, a cable goes straight up. This cable is the heart of the elevator. It stretches up past the atmosphere, past the orbits of most satellites, and into a region called geostationary orbit, or GEO. The geostationary orbit is the magic altitude. It's about 35,786 kilometers straight up. At this specific height, an object orbits the Earth at the same speed the Earth is turning. So, if you put a satellite there, it just hangs over the exact same spot on the ground all day, every day. Your satellite dish at home points at a satellite in GEO. This is the balancing point for the elevator. But the cable can't stop there. If it did, gravity would just pull the whole thing down. You need to keep it tight. To do that, the cable has to continue much further out, another 60,000 kilometers or so. At the very end of this cable, you place a massive counterweight. This could be a captured asteroid or a big space station built for the purpose. Now you have a cosmic tug of war. The lower part of the cable, below geostationary orbit, is being pulled down by Earth's gravity. It wants to fall. The upper part of the cable, the part extending way out past Geo with the heavy counterweight on the end, is spinning around the Earth. Centrifugal force, the same force that pushes you to the side when you take a sharp turn in a car, is flinging this upper section outward, away from Earth. The whole system is designed so that the outward pull on the top half is slightly stronger than the downward pull on the bottom half. This is what keeps the cable perfectly taut, like a piano wire stretched between the Earth and the counterweight. It's not a tower pushing up. It's a tether pulling down from space. With the cable in place, you can send climbers up and down. These are the elevator cars. They wouldn't be pulled by cables like a normal elevator. They would be self-powered, using wheels to grip the main cable and climb it. Most designs propose powering them from the ground. A giant laser at the anchor station would shoot a powerful beam of light at solar panels on the bottom of the climber. This light would be converted into electricity to run the motors. The trip wouldn't be fast. It would take about a week to get from the ground to geostationary orbit. It would be a slow, steady, and incredibly efficient ride to space. In theory, this all works. The math checks out. Konstantin Tsiolkovsky, a Russian rocket scientist, first imagined the concept in 1895 after seeing the Eiffel Tower. He imagined a tower to space. Later, others refined the idea into the hanging tether we just described. So, if the physics is sound, what's the problem? The single biggest showstopper, is the cable. It's all about the material. Think about what this cable has to do. It has to support its own weight for 100,000 kilometers, while also being strong enough to handle the pull of the counterweight, the strain of climbers moving up and down, and the forces of nature. The key property here isn't just strength, but what's called specific strength. That's a measure of how strong a material is for its weight. Let's think about steel. Steel is strong. We build bridges and skyscrapers out of it. But it's also very heavy. If you try to build a space elevator cable out of steel, it couldn't even support a few kilometers of its own weight before snapping. The same goes for Kevlar or any other material we currently use to build things. They are all far too heavy for their strength. The cable would break under its own weight long before it ever reached space. For decades, this is where the conversation ended. The space elevator was impossible because no material could do the job. Then, in the 1990s, something changed. Scientists discovered carbon nanotubes. Carbon nanotubes, or CNTs, are microscopic. They are tiny, hollow tubes made of carbon atoms arranged in a hexagonal lattice, like a rolled-up sheet of chicken wire. and on paper they are the miracle material we've been waiting for. They are incredibly light, and they are theoretically one of the strongest materials that can exist. Their specific strength is off the charts. A single perfect carbon nanotube is strong enough to build the space elevator cable. In fact, it's many times stronger than what's needed. This discovery is what moved the space elevator from pure fantasy to a remote engineering possibility. Suddenly, the biggest obstacle seemed to have a solution. The dream was alive again. But there's a huge gap between theory and reality. Here's the problem with carbon nanotubes. We can make them in a lab. We can make tiny, perfect, incredibly strong ones that are a few centimeters long. But we need to make a cable that is 100,000 kilometers long. That's 100 million meters. We have absolutely no idea how to manufacture carbon nanotubes on that scale. It's like knowing how to make a single perfect brick, but having no idea how to build a skyscraper. Even if we could produce them in bulk, the challenges are immense. The strength of CNTs comes from their flawless atomic structure. But when we try to make them long, defects creep in. A single missing atom or a mistake in the lattice can create a weak point. And in a structure like a space elevator cable, the entire system is only as strong as its weakest point. A single flaw could cause the whole thing to snap. Scientists are working on ways to weave shorter nanotubes together into a composite ribbon or thread. But this process also introduces weaknesses. The bonds between the individual tubes are never as strong as the tubes themselves. Right now, the strongest carbon nanotube fibers we can actually produce in a lab are still nowhere near strong enough for a space elevator. We are not even close. Other materials are being explored. Boron nitride nanotubes have similar theoretical properties. The diamond nanothreads, which are like ultra-thin strings of diamond, are another possibility. But they all share the same fundamental problem as carbon nanotubes. We can only make them in microscopic quantities in a lab. There is no known industrial process to create kilometers, let alone hundreds of thousands of kilometers, of this material. So the material is the first and biggest hurdle. Until we have a major breakthrough in material science and manufacturing, a breakthrough on the scale of the invention of steel or plastic, the space elevator simply cannot be built. It's a complete non-starter, but let's be optimistic. Let's imagine that tomorrow a scientist announces a new process to cheaply mass produce a flawless kilometer-long carbon nanotube ribbon. The material problem is solved. Can we start building? Not so fast. The material is just the first of many giant problems. Even with the perfect cable, a space elevator would be the most complex and fragile structure humanity has ever attempted. And there are a million other ways it could fail. Let's talk about space debris. Our planet is surrounded by junk. There are dead satellites, old rocket stages, and millions of tiny pieces of shrapnel from past collisions, all zipping around the Earth at speeds of over 28,000 kilometers per hour. At that speed, a fleck of paint can hit with the force of a bowling ball. A loose bolt has the energy of a bomb. The space elevator cable would be a stationary target in this cosmic shooting gallery. It would be a thin ribbon, maybe a meter wide, but 100,000 kilometers long. Over its lifetime, it would be guaranteed to be hit. A small impact might just sever a few fibers, which could be repaired, but a larger impact could sever the entire cable. How do you protect against that? Some have proposed that the elevator would have to be able to move. The anchor station could be a massive floating platform in the ocean, allowing the base of the cable to be shifted out of the way of predicted impacts. The cable itself might need thrusters along its length to nudge it, but this would require a tracking system of unimaginable precision. We can't track every little piece of debris up there. We don't even know where most of it is. A single untracked marble-sized piece of junk could destroy the entire multi-trillion-dollar project. And there's the weather on Earth. The anchor station has to be on the equator. Many equatorial regions are prone to severe weather, like hurricanes and thunderstorms. A hurricane could destroy the ground station. A lightning strike could send a massive surge of electricity up the cable, potentially frying the climbers or damaging the cable itself. The base of the elevator would need to be in the most geologically and meteorologically stable place on Earth. And even then, you can't guarantee its safety. The cable itself would also face its own kind of weather in space. Solar wind and the Earth's magnetic field would push on it. The gravity of the sun and the moon would tug on it. These forces would cause the cable to vibrate and oscillate. It would sway back and forth like a colossal guitar string. These vibrations are a serious threat. If they build up, a phenomenon called resonance could occur, where the oscillations get bigger and bigger until they whip the cable so violently that it snaps. The elevator would need a complex system of active dampeners to counteract these vibrations. These could be thrusters on the cable or mechanisms within the climbers that move in a way that cancels out the waves. This is an incredibly complex control problem on a scale we've never attempted. And what about powering the climbers? The idea of using a ground-based laser is popular, but it has its own issues. The laser beam would have to travel through the atmosphere. Clouds, rain, or even just atmospheric turbulence could scatter the beam, cutting off power to the climber and leaving it stranded. You would need multiple laser stations spread out over a large area, ready to take over if one is blocked by weather. And the laser itself would have to be phenomenally powerful, raising concerns about safety for any aircraft that might fly through its path. The efficiency of the solar cells on the climber would also be a challenge, as they would need to convert light into motion with very little waste heat. Then there's radiation. As the climber slowly ascends, it has to pass through the Van Allen radiation belts. These are zones of highly energetic charged particles trapped by Earth's magnetic field. They are dangerous. Satellites are hardened to survive them, and human missions like the Apollo flights blasted through them as quickly as possible. But the elevator climber would spend days, not hours, crawling through these belts. Any humans or sensitive electronics on board would be exposed to a lethal dose of radiation. This means the climbers would need to be heavily shielded, but shielding is heavy. Heavy climbers put more strain on the cable. A stronger cable needs to be thicker and heavier itself. This creates a vicious cycle where every solution adds more weight and more complexity to the whole system. So even if we had the magic material, we would still face monumental engineering challenges. We would need to solve the problems of space debris, terrestrial weather, cable vibrations, power transmission, and radiation shielding. Each one of these is a massive undertaking on its own. Solving all of them for a single, interconnected system is a challenge of a completely different order. But let's keep dreaming. Let's say we solve the material science and all the engineering problems. We have the perfect cable, and we know how to protect it. Now we face what might be the hardest problems of all the human ones. First, the cost. Building a space elevator would be the most expensive project in human history. Estimates vary wildly, but they are always in the trillions of dollars. Some say it could be as low as 1 trillion, others say it could be 10 or more. Who's going to pay for that? No single country has a budget for that. No single company, not even the biggest tech giants, could fund it. It would require a global consortium of nations and corporations working together for decades. This leads to the second problem in geopolitics. A space elevator would be a gateway to space. Whoever controls the elevator controls access to the high frontier. It would be an asset of immense strategic and economic importance. Which country gets to have the anchor station on its territory? Who gets to set the prices for a ride to orbit? What happens if the country that controls the elevator gets into a conflict with another country? The elevator itself could be seen as a weapon. From geostationary orbit, simply dropping a dense object, like a tungsten rod, would result in it hitting the ground with the force of a small nuclear weapon, but with no radioactive fallout. The potential for rods from God is a terrifying military application that would make every nation nervous. The project can only happen in an era of unprecedented global peace and cooperation. Given the state of the world today, that seems like a bigger fantasy than carbon nanotubes. Then there is the issue of security. The elevator would be incredibly vulnerable. The anchor station would be a prime target for terrorists. A single, well-placed attack could bring the whole thing down. Even the cable itself, while in space, could be a target for a hostile nation. It is a single point of failure for the entire system. How do you protect a structure that is 100,000 kilometers long? You can't. You have to rely on treaties and the goodwill of everyone on the planet. And that brings us to the most terrifying question of all: what happens if it breaks? The outcome depends on where the cable snaps. If it breaks at the anchor station on the ground, the entire cable and counterweight would be flung outward. The centrifugal force would be unopposed by the anchor, and the whole thing would fly off into a higher orbit or escape Earth's gravity altogether. This would be an astronomical financial loss, but it wouldn't directly harm anyone on the ground. But if the cable breaks anywhere else, especially at or near the counterweight, the scenario is much, much worse. The lower portion of the cable would lose the tension holding it up. It would fall back to Earth. But it wouldn't just fall straight down. It would be moving at orbital velocity. As it fell, it would wrap itself around the planet along the equator. Imagine a whip, 35,000 kilometers long, made of the strongest material in existence, lashing across the surface of the Earth at thousands of kilometers per hour. It would cut through anything in its path, cities, mountains, forests. It would cause a path of destruction on a scale never seen before, a scar circling the entire globe. The sheer energy released would be catastrophic. This single horrifying possibility might be enough to ensure a space elevator is never built. The risk of a failure, no matter how small, is simply too great. So, after all this, is a space elevator a feasible idea? The honest answer is no, not right now, and maybe not ever. The obstacles are just too numerous and too large. The material science isn't there. The engineering challenges are on the verge of impossible. The political and financial hurdles are colossal, and the safety risks are terrifying. However, that doesn't mean the dream is completely dead. It just means that an Earth-based space elevator is likely not the first step. A more feasible starting point might be a lunar elevator. The moon's gravity is only 1/6 that of Earth's. It has no atmosphere, which means no weather and no atmospheric distortion for power lasers. It has a much less cluttered orbital environment. The materials required for a lunar elevator wouldn't need to be nearly as strong as for an Earth-based one. Or we could probably build one with materials we can already produce, like Xylon or Kevlar. A lunar elevator could be a fantastic way to transport materials mined from the moon up to a central space station, which could then be used for construction or fuel. It would be a proof of concept, a way to test the engineering and control systems on a smaller, less risky scale. Similarly, an elevator on Mars is also more feasible than one on Earth. Mars has lower gravity and a thin atmosphere. It could be a key piece of infrastructure for a future Martian colony. But what about here on Earth? Is there any hope? Perhaps the question is changing. The main reason to build a space elevator is to dramatically lower the cost of getting to orbit. For decades, launching things on rockets has been incredibly expensive. The elevator promised a cost of just a few $100s per kilogram. But now we have companies like SpaceX with reusable rockets. The Falcon 9 has already drastically reduced launch costs. Their new Starship vehicle, if it works as designed, promises to lower them even further, potentially to a few $1,000,000 per flight. While that's still not as cheap as a space elevator would be, it's a massive leap forward. Reusable rockets are a technology that works today. They are making access to space cheaper and more routine. This might change the economic calculation. If rockets become cheap enough, the gigantic investment and risk of a space elevator might not be worth it. Why spend trillions on a fragile, vulnerable cable when you can just use a fleet of reliable, reusable rockets? The one area where an elevator still holds a unique advantage is in lifting truly massive quantities of material. If we ever want to do something like build giant solar power satellites in orbit to beam energy back to Earth, or construct city-sized space habitats, we would need to move millions of tons of material off planet. And rockets, even cheap ones, might not be practical for that kind of bulk transport. That might be the ultimate niche for the space elevator. It's not for launching a few satellites, it's for industrializing space on a scale we can barely imagine. So where does that leave us? The space elevator is an elegant and powerful idea. It represents a different vision of our future in space, one based on quiet, clean, and continuous connection rather than violent, episodic launches. The physics works, but the practical barriers are, for now, insurmountable. We can't make the material. We don't know how to solve all the engineering problems, and we probably can't manage the cost and politics. It remains a benchmark for our technological ambition. It's a challenge problem for future generations of scientists and engineers. Perhaps one day, a breakthrough in nanotechnology will give us the material we need. Perhaps new computer systems will be able to manage the complex dynamics of the cable. And perhaps humanity will reach a level of cooperation where such a global project is possible. But for now, and for the foreseeable future, the space elevator will stay where it has always been a beautiful idea, waiting just over the horizon of what is possible. It's a dream of a quiet road to the stars, and while we will continue to reach for space on pillars of fire and smoke, we can still look up and wonder what it would be like to simply ride an elevator all the way to the top.